Well, this is the official good morning, everyone. Welcome to Resilience 2020. This is our 13th workshop in resiliency. I guess that's a special one for me since I always considered 13 to be my lucky number. And we're held in conjunction with Europar 2020. And I wish we were in Warsaw, Poland. Unfortunately, because of circumstances, as everyone knows, we're doing this as a virtual workshop. So I'd like to welcome you and thank you very much for joining us today. I'm pleased to see we have a number of folks, and we've had a number more join us in recently. There we go. So our mission for this, for longer than even the 13th, and we'll get into that for a moment, has been to look at the challenges with respect to resilience in high performance computing. This is one of the areas that a number of us have worked in for myself for my entire computing career, and we've extended it over time to include other areas such as we mentioned here in clusters, clouds, and grids. Originally, many of us that were involved in this were from the high performance computing realm, which did not look at including cluster, clouds, and grids. But that component has come in as we've broadened our view, and as well as high performance computing has broadened its view over time. And one of the problems some of us that had either come from national laboratories or worked in national laboratories is we had a very big hardware centric excuse me, viewpoint of looking at high performance computing, and over time we broadened our view and broadened our understanding of high performance computing. And today I kind of say high performance computing is in the eye of the beholder to a certain degree, because as I moved to university and did more work with the university, sometimes high performance computing is a significantly large machine that has the ability to solve someone's problems. And so that's expanded the view of the workshop quite a bit over the years. We have a pretty rich history, as I said, going back. We had some workshops that went back all the way back to 2003, where we held what we called HAPCW, and this was held for a number of years with something called LASKI, which was a Department of Energy in the U.S. Program, and they sponsored us, as we have with the Europar workshop conference. And so we held those for a number of years, and this was kind of the proving ground, or looking to see, testing the waters of where the problems were, where the issues were that we were looking at. Then we had something we also called the Resiliency Summit. This was a little bit different. Many of the same early participants were involved in the Resiliency Summit, and this was an invited talk format. We had as I would say, the luxury of looking at areas that we thought were of interest in high performance computing and resiliency, and we would get those folks together, as well as invite others to listen and look at where we felt the significant problems were. And then we go to the workshop on resiliency and high performance computing, this workshop. The history goes back quite a bit, back to 2008. Originally, we were hosted with a couple of other organizations trying to find our home as it is. And in about 2011, we started with the Europar conference. And one of the reasons why we were very interested in getting to a non-US based conference was that we wanted input from other folks than our peers within the US, broadening our horizons, as you will. And so in addition to that, in joining Europar, we found a great home, a great partner, and also we achieved getting that diversity of thought that we were looking for with other folks outside of the US and typically outside of the pure HPC community that we had within the US. And we've had a number of great locations that we were actually able to visit. And I was looking forward to 2020, the 13th, going to Warsaw, but unfortunately, as we said, we're virtual. And if you take a look at the links that I have included here, and I think we have one on a previous slide, you can actually go back and find the talks and the material from those workshops if you want to go back and take a look at those. Unfortunately, the HAPCW that we held earlier, I don't believe those are online any longer. They were hosted at a university, and I believe they're gone. If there were some papers you were interested in, we may be able to find those. But here we are today, as I said, 2020 with the 13th, lucky 13 for me. And I want to thank my co-chair, Christian Engelman from Oak Ridge National Laboratory. Christian has worked since day one on all of these workshops with me when I was at Oak Ridge, and when I moved to Tennessee Tech, he continued to work with us and has provided a leadership role throughout. Our program chairs this year, Thomas Naughton and Farrell Adderholt, have done a great job in putting together our program and dealing with reviews and the logistics of things taking place. And then I have to thank Chakchai Box Ling Suk Sung from Louisiana Tech University. He and I are colleagues that go all the way back to graduate school, which was longer than I'll probably admit. And Chakchai and I worked together originally as the general chairs on the workshop, and with Christian moving into that role more recently as Chakchai is moving on to other things in life. I'd like to thank our program committee, who did a great job in reviewing all the papers, and that's vitally important, more important than in some ways than those of us that do the logistics of the workshop. One of the things I noticed when I was putting all this together is and I want to mention this now, I would like to see more reviewers and more people involved from outside of the US. We have a number there, but I would like to see it more balanced at some point. We still tend to be dominated a bit by the US high performance computing community. So that would be nice. If you're interested in joining, you can send me an email or Christian an email and let us know. Our plans are to go forward and continue on with the 14th and beyond. We have this year a number of areas of interest, and I'm not going to go through all of these, but we were looking at some theoretical foundations that allows us to look at models and performance and things in that area. And then error failure, anomaly detection, and reliability, dependability modeling. And we're looking at some analysis of the models and the behavior. And we're interested in that area, expanding, looking at a popular area now, looking at machine learning and artificial intelligence with respect to resilience in high performance computing. Monitoring and control. Here we're looking at basically the systems of how to physically deal with the reliability and reliability issues. And end-to-end integrity, looking at design center systems, applications, what occurs throughout the process when we're looking at resilience and as things begin to fail, how it degrades. Infrastructure, looking at the system side again, from the software, middleware, the infrastructure software to make that happen, and resilience algorithms, of course, looking at the actual code, the systems as well as the application side of things. Excuse me. Our program this year, we're in the opening now. We have 30 minutes for that. We have 30-minute time slots for about everything. We have a keynote. We have 3 regular papers that were peer-reviewed and accepted for our half-day workshop. There's a coffee break mixed in there, which is after the keynote and one of the papers. By coffee break, yes, you can go get coffee, but it also gives you 30 minutes to do anything else you may need to do, as well as consider this a coffee break if you were at a workshop, in the sense that gives you the ability to chat with other folks using Slack, I believe is the forum for that. And then at the end, we'll have an additional discussion about the workshop and going forward, as well as an open discussion. Unfortunately, you know, at that point, we would, in person, typically a bunch of us would go off to lunch and continue discussions. Unfortunately, we don't have that luxury this year, which is too bad. So our program, as I said, we're currently in the opening, and here I have only 2 time zones posted, hopefully in the sense that in the US, I can base wherever I'm at based on the Eastern time zone, and I'm hoping those of you elsewhere can do so from the Central European time zone. But as we have 30-minute time slots. We'll be followed by the keynote and the first paper in this current session, and then we'll move on to, as I said, we'll have a coffee break, followed by the last 2 papers in the second session, and then an open discussion. With that, I will hand things over to Christian Engelmann, my co-chair, and he will provide us an introduction moving into our keynote. Christian?
All right, this is Christian Engelmann from Oak Ridge National Laboratory. I would also like to welcome everyone to this virtual workshop. Unfortunately, we are not in Warsaw. I was also looking forward to visiting Poland. But I want to make sure that everyone is aware of the technology we're using, the format we're using. So all the panelists, all the speakers should be basically joined via the Zoom session so that they can be promoted to a speaker and can then also share their screen when needed or talk when needed. The attendees will not be promoted to that capability, but rather have the option of either using Zoom in the webinar form where they're just getting the video and audio stream, or they can use the corresponding YouTube live stream. YouTube scales a little bit better. So if you're getting problems with Zoom, just go over to the YouTube live stream. And you can find all of this information in the Slack space and the Slack channel of the Resilience Workshop. We will be using Slack for the attendees to ask questions to the speakers, also during the Q&A session and also during the coffee break. We can use this quite freely to just talk with each other. You should have all, while signing up with the Europar conference, received access to the Europar 2020 Slack space. And within that Slack space, there's a Slack channel called W05-Resilience. And within that Slack channel, all the discussions will be held pretty much by the attendees that do not have direct access to the Zoom session. The reason for the split of sort of having Zoom for the attendees and panelists, Zoom for the panelists and speakers, and having Slack sort of for communication between the attendees was to have more scalability. Because once we basically scale Zoom to a certain amount of speakers that can talk and so on, they start getting issues. And if you haven't heard yet, Zoom actually yesterday crashed in the morning worldwide from what I have heard. As I said, we basically will do this, or Stephen said, we will basically do this one talk after another. We will have first the keynote and then one paper and then a coffee break and then 2 more papers. After each of these talks, which are pre-recorded videos that will be played by the host, we will have a few minutes for just some questions and answers via Slack. These questions can be asked via Slack, and then the speakers or corresponding co-authors that I've joined can sort of answer the questions. So this is sort of the overall format of this, and we still have a few more minutes. I would like to wait a few more minutes. Maybe other people will join a little bit later. In the meantime, I will talk a little bit about resilience from my perspective at Oak Ridge, and so that you can get a little bit of a feel of where we're coming from and what this workshop is about and where maybe this will go into the future. We can then discuss this later on today in the question and answering session as well. So Oak Ridge National Laboratory, where I'm at, where also Stephen originally was at, is one of the large US Department of Energy research laboratories that has had a supercomputer for decades. We have always had a supercomputer that was within the top 500 list. And within the last 20 years, we were always with somewhere between the #1 or #5 of the top 500 list. So we always had sort of one of the fastest supercomputers in the world. And the biggest issues we experienced was that while we're having these large-scale supercomputers, we were also dealing with errors and failures in these systems. And every time we got a new generation, every 3 to 5 years, we got a new generation of supercomputers. We dealt with different kinds of errors or failures. These can range from problems with the power supplies to networking issues, also to just basic component burnouts over time. I also want to make people aware that I have a paper that was accepted at the Supercomputing conference that is held in November, where we will be talking about a ridiculous number of GPU failures we had. I want to caution you, everybody, it's not the GPU itself that initially failed, but a tiny resistor right next to the GPU was failing over time. And since that resistor was providing a reference voltage, it was basically over time increasing that reference voltage, and the GPU basically got cooked over time. And this was with our old supercomputer called Titan. Titan had over 18,800 GPUs. And out of those 18,800, we had to replace 11,000 out of them, because most of them were severely damaged and didn't work anymore, and the others were basically on their way out. So you can see this is sort of a really severe problem we're facing with resilience in these large-scale systems. At the same time, we are also sort of looking at other systems that are not necessarily large-scale, but have to provide reliable services. These can be clusters, these can be cloud computing environments. These days, a lot of things in computing require sort of reliable computing. And there are a lot of different aspects when it comes to these kinds of things, especially when we go down to the root causes of what causes these failures, and then see that the root causes over the next several years will get worse and worse, and we will need to deal with this. So we now have sort of given a little bit of an introduction overview of what we're going to talk about in the next few minutes. And we will be now switching over to the keynote. And I would like the host to share already the YouTube playlist, the first video, which is by Petar Radojkovic, if I speak the name correctly. Peter is a memory systems team leader at Barcelona Supercomputing Center. He explores various aspects of memory systems for high performance computing. Memory resilience is an important part of his research, and he participated in various European high performance computing projects. And he was leading projects with major memory manufacturers like Micron Technologies and Samsung. And he has got his PhD from UPC in Barcelona, also his master's degree actually there. And I'm happy to basically welcome his talk as a keynote session for this workshop titled Towards Resilience, EU HPC Systems, a Blueprint. Please play the video, thanks.
Center. And today I will talk about some work done in Europe in the field of HPC resilience. The objective of this talk is that you download and read this document. And I have two strategies for this. First one is a hypnosis GIF that I found online and ridiculous color scheme. And if it works for you, that's just great. It's a shortcut, so just download the document, read it, skip the rest of the talk. If the hypnosis GIF did not work for you, surprisingly, I have another strategy. And this is to tell you actually the real story behind this work. And the real story is that indeed we did release the blueprint. It's there, you have a link, you can go download it, please check it. It is a work from numerous resilience experts, 30 of us were working on it. We believe that this document is important, needed, that it was missing, and we find it useful. And on the talk today, I will give you a brief outline of this talk, but more important, I will try to give you a story behind it, to explain you why we did it and why we did the things in the way that we did. The story started somewhere in 2015, 2016. What you see on your screen is part of the call for projects published in October 2015 in the area of HPC in Europe. And the 6-line summary that you see is the expectation of this call from us. So what should we deliver? Summarized in 6 lines. And what you see already in the first line is that we should build the highly resilient HPC platforms. And a bit below, underlined in red, is that designs must respond to critical demands of resilience. Again. So I assume that this is not a surprise for you, because if you check strategic research agendas in Europe in the last decade, they all agree that system resilience is one of the most important exascale challenges. Also, these agendas agree that system resilience is a vertical problem that requires holistic solutions. And if you leave Europe, if you go worldwide, for example, to the US and check the US Department of Energy agendas, you will find the same message. HPC resilience is a vertical problem and it requires holistic solutions. What does it mean? It means that we are dealing with a multi-dimensional problem, that we cannot solve it in one place. So we need to do it in hardware, in system software, in applications, in the way that we think about our algorithms. In the table below, you see various RAS features, such as failure detection, reporting, recovery, redundancy, and so on. And you see a list of components, such as CPU, memory, FPGA as a representative of merging accelerators, and so on. For each of these system components, there are various resilience features we can think about. And all of them together, so all these features for each of the components should work together to give us something that should be a holistic resilience system. In Europe, we were working in the field of resilience. It's not a new topic that we should cover, so we are not completely in dark. However, if we see the research done in the previous projects, we will see some sparse and unconnected research areas. This is a serious issue because if you have a holistic problem, you cannot solve it with local approaches. Let's make an example of airbag in a car. So if you see the figure below, we have various steps. We have a failure, that would be a car collision. Then we need to detect this collision. And then if we decide that this collision is severe enough, we can activate or deploy an airbag as a way to mitigate the failure. Obviously, I mean, if you have an airbag but you cannot detect your collisions, this system is useless. And you may think that it is a ridiculous example. But yet, if you try to find analogy in HPC projects and prototypes we were building in past, you will find a lot of projects that had some research very exotic and advanced research. For example, trying to find the optimum gas that would deploy an airbag, but prototypes that at the same time had no way to detect failures whatsoever. Let's make one more parallel between car safety and HPC resilience. In most countries in the world, if you want to use your car in public transport, the car has to comprise some safety features. There is a list of must-have features for the car. Is it resistant glass, safety belts, lights, mirrors, bumpers, so on. It means that if you do not have these features, you cannot use your car. It is not considered to be safe. In HPC, unfortunately, this list doesn't exist. So if we can think about an HPC car and any resilience that this car should include, we can think about the car without glass, without belts, without lights, without mirrors, and no bumpers. And there will be no document that this car would violate. And this is a serious problem. It is so serious that it gathered all the people you see on the screen to think together how we should try to solve it. It is very interesting that most of us in this list actually do work in European projects. And actually we are the ones who are trying to put the label resilient to these projects. We are working in our corners, trying to take care about some very specific resilience aspects. And we're trying to do this well. But at the same time, we accept that by just keeping each of us in his corner, it is unlikely that we will provide resilient HPC systems anytime soon. We agreed about the problem, but what about the solution? If you see this house, it has many problems. With the roof, walls, front door, windows. But if I ask you to state what is the fundamental issue, what is the problem that causes everything else, and what is the problem that we should solve first, I hope that you're looking here. And this is something that we are trying to do also in resilience HPC research in Europe. We believe that setting good foundations for any future HPC resilience is the most important thing we should do at this point. And this is not intuitive. This is not just straightforward, doing more of the same we were doing in the past. This is something completely different. We are aware that this will not maybe be considered research. We are aware that this will not bring us top-level publications. But we strongly believe that this is what we have to do. Setting these foundations requires 3 steps. First, we have to understand resilience-related characteristics of HPC applications and systems. Some of these characteristics will be obvious for you. Maybe most of them will be obvious. But some of them might be a surprise. Step 2, we have to analyze the resilience features of state-of-the-art HPC systems. And this is not reading the papers. This is not Google Scholar. This is understanding what do we have in the mainstream HPC servers today. Step 3 is once we have this list, and it will be a long list of resilience features that we have today, we have to understand which one of them should have the highest priority to be implemented in European HPC. The outcome of this work is a list of must-have HPC features. Must-have features for something that should be a building block for future European exascale. Just to be clear and explicit, in this document and in these slides, we cover CPU, memory, and FPGAs. This is because the projects who initially funded this effort was focused on this. We are already working on other HPC building blocks, such as interconnect and storage, and we plan to release this data soon. The most important word we should keep in our mind when thinking about resilience-related characteristics of HPC systems is the cost. cost in euros, dollars, or at least server hours that we have due to the scheduled and unscheduled system repairs, corrected and uncorrected errors, detected and undetected failures. We should also keep in mind the cost of the resilience features that we try to use to mitigate the impact of these repairs, errors, and failures. And then we have to compare the cost of our disease with the cost of the remedy that we propose. I will try to emphasize the importance of thinking in terms of cost with an example that bothers me for some time. The cost of corrected DRAM errors in production is effectively zero. I know that some of you will complain. You can come up with examples where especially a large number of these errors can cause some troubles. But effectively, their cost is zero. The cost of uncorrected DRAM errors is high. For each of them, we have to reboot the server, we have to kill the HPC job, and all the server hours from the beginning of this job or from the last checkpoint are lost. If we see the academia, however, and we see the number of studies that analyze these errors, for each of them that deals with uncorrected DRAM errors, we'll find maybe 10 or 20 of the studies that deal with corrected errors. An obvious question is why. This, for some of us, paradox, however, is obvious only if we think in the terms of cost. And this is why it is important. However, this way of thinking is typically overlooked, and for this reason we emphasize it so much. The second step is understanding the state of the art. But with this, we do not refer to reading the latest scientific papers in this field, but understanding the state of the art in production HPC systems. These features are listed in the documents published by Intel, ARM, and OEMs. And we have to understand them well because they are the gold standard by which the EU HPC resiliency will be measured. As the third step, we should have a clear position about each state-of-the-art resilience feature. Why is this important? Mainstream HPC companies such as Intel, for example, were developing their solution for decades. We cannot pretend that in the first European prototype we will implement all the resilience features that they have. For this reason, it is important to make a clear selection between the features that we must have in our production system at least, from the ones that require cost-benefit analysis, or maybe the ones that are not so essential for now. This is a very complex problem, and I will not enter into the details how we actually did it, but it requires understanding of the HPC RAS requirements, and it again comes down to the cost of the system failures and the corresponding resilience features. And this is the outcome of our work, the list of the must-have HPC resilience features for CPU, memory, and FPGAs. I will give you a minute to go over this list. At this point, you're probably asking yourself, what is so novel about these features and what is the value of this work? And you're right, there is nothing novel about these features. We took them from state-of-the-art documents. But the value of this list is that it has only 11 items. We started with maybe 50 documents with hundreds of CPU, memory, and FPGA resilience features, and we selected only 11 ones that we consider must-have. We believe that this list is a great starting point if you're planning to make something that would be a building block for European exascale HPC. It will help you to understand which resilience features you had in mind and maybe to detect the missing ones. Also, it is a great way for reviewers to quantify the resilience of the overall solution. Some of you may argue that the work that I presented is not research. And I agree with you, it's not. At least it's not research we are used to see. However, I hope that we can all agree that it is important, it was missing, and it is useful. It is important because the platforms that lack holistic resilience are not production HPC platforms. They cannot be considered even a building block for a production HPC system. It is missing because the EU-funded research on resilience was scattered and unconnected, and this was not a road towards resilient HPC. For example, we did not even have a document with the list of the must-have resilience features. I spent a lot of effort arguing with some of the people driving European projects on whether or not the error correction codes in memory should be included as a must-have feature in these projects. Now, at least I have a document that confirms my opinion. Finally, it is useful because it helps us to understand where we are in terms of resilience with respect to the state-of-the-art systems and where we should invest our effort. And this is important for the researchers, but also for the policymakers to understand where the fundings should be invested. Finally, a checklist of the resilience features we delivered is very useful for future HPC prototypes, pilots, and production systems. It is important for the people who are planning and deploying these systems from the project proposal level until the final delivery, and also for the people who are reviewing the proposals and deployment of these systems. To summarize, I hope that we all agree that HPC resilience requires holistic solutions. I also hope that we understand that sparse and unconnected research will not bring us these solutions. A good news is that the HPC resilience experts in Europe, together with our colleagues from the US, gathered around this problem and around the general idea. We understood that the first thing we should do is to set some boundaries for any future R&D work in this area. As the first outcome of this work, we have recently published a document that I shamelessly announced at the beginning of this talk, in which we summarize the main ideas toward resilient EU HPC systems in Europe, the first steps in this direction, and the first outcomes. If you have any feedback or comments about the document or about the talk today, please come back to us. If you're listening to this talk, it means that you're part of the community, and we really need your help to keep moving and improve. This talk is recorded for a keynote at the Resilience workshop held in conjunction with the EuroPar Conference 2020. The Slack and Zoom Q&A session will follow. If you're watching the video after the conference, be free to contact me over my email. I'll be happy to come back to you. Stay safe, stay resilient.
Okay, so let's do a virtual thanks to our speaker. This is Christian Engelmann again. Yes, I would like to personally thank Petar for this keynote. This is a document that, as you can see, a lot of people have worked on over quite a significant amount of time. And it was sort of designed as creating a baseline of what needs are in Europe in terms of HPC resilience and HPC resilience research. And if you have any questions, feel free to ask them via the Slack channel or via, if you are, and Stephen should stop pinging me. If you are already on another speaker, you can also, of course, talk via Zoom if you would like. Peter, you can also unmute yourself and say additional things if you want. The one part of this idea of this keynote was to make people aware of this document that has been written up by this group of people, and to circulate it in the broader community. Please take a look at it. And see if it makes sense to you. Also, give people give us feedback. This may eventually even get published potentially as another journal paper, maybe in a more engineering type journal. But it's important work, I think. So, are there any questions?
So just a brief comment from my side. I mean, first, I mean, for the organizers, I mean, thank you for working on this. Thank you for working on this in difficult times. It will not be optimal workshop or perfect workshop, but we have to keep moving. It is what it is. I mean, and we just have to keep moving this way. And it's happy that I'm glad that actually even in these tough times, technology helps us to keep moving. So that's great. I mean, something that we are looking today also is this, and we were looking with this document, is this, as Stephen mentioned, diversity of thought. I mean, sometimes, I mean, and it's funny that actually when Stephen started, he said, okay, we wanted to go to Europe to see what those Europeans think about this, to get some new ideas. And from Europe, I think that we have to learn from others. I mean, especially US probably. And because you say you had supercomputers for decades, you have so much experience on this, and we are so behind. I mean, we have to be honest that we are so behind, and we have to start with the basics. And there are so many things we can learn from you, and it's great that you are part of this team. Also, it's great that we have other experts from US, and I hope that we will also keep learning from you in future. And these workshops, although virtual, are a good place to keep this discussion and keep learning from each other. That's all for now. And obviously all the questions you can go over Slack now or whenever, and I will be here during the whole workshop and during the Q&A session.
Yes, so we have one question from Thomas. In the must-have list, you mentioned CPU frequency scaling. Can you elaborate on the resilience aspect here?
Okay, so here I am. So if you see some bark in the background, sorry, it's yes, one of the something that I did not enter in this in this talk is what was the rationale behind these resilience features. And you will find this CPU frequency scaling, and you will find also other resilience aspects that are related to thermal issues that we may have. And one of the things that we decided is that thermal aspect of resilience is very important for us, and that we have to cover all of them. So this is also memory frequency scaling, CPU frequency scaling, and so on. So for this reason, I mean, if you will find more info on this in the document. And did I at least Thomas, is this okay for you, or should I keep talking? Great, good. But anyway, I mean, something that is important for us, and I want to be super clear. This is not the end of the road. I mean, and even the statements that we made in this document, it's not like, no, this is written and it will be like this forever. I mean, please come back to us. We are trying to move this initiative in Europe, and help us. I mean, if you think that, I mean, if you have any comment, come back to us. you have more experience. I mean, help us do something useful here. I mean, Europe is doing a lot of things in HPC. We are talking about European Processor Initiative, about ARM, about RISC-V, about all the things that are new. This is great. But I mean, we have to understand this is really big thing, and any help from the outside is great. That's all. Also, Manolis posted a comment about the document, about the link where you can get it. Manolis is one of the guys who was here from the beginning, and it's thank you, Manolis, for being here today. And also, if you contact Manolis, it is great. And any of the people who are in editorial board will be happy to answer your questions.
Okay, thanks. Are there any other questions? If not, so I have one. What do you think are the next steps beyond this document?
We already, I mean, as one I mentioned during the recorded talk today, is that we covered only CPU memory and FPGAs. And I mean, the first question you may have, we may ask why FPGAs? Because at some point FPGAs were considered, and it still are considered, one of the interesting accelerators that might be used in HPC. And then, I mean, similar-ish maybe to the GPUs, but I mean, a couple of steps behind. So these are the things that we did cover. So we did not cover everything else. So we do not have our, let's say, official position at this point about storage, interconnect, and so on. This would be the first thing to do. And let's see whether we have some material, and I hope that this would be the next step. Let's see what happens. Let's see whether we also find some funding to keep this moving, whether we keep some interest among the people, and let's see what happens here. Thank you, Christian, for asking.
Yep. All right. Thanks. Any other questions? So from the US perspective, it's interesting to see that oftentimes resilience is sort of relegated to the vendor or the integrator. So either the company that produces the components or the company that actually assembles the components into the HPC system. And we often then give them sort of specific parameters in terms of your system needs to achieve this type of a mean time to interrupt, or this time of an availability, meaning uptime. And while this is typically then achieved when the system is on the floor and just deployed, a few years down the road, we start seeing resilience issues that were unanticipated and that basically then violate the original contract, but we can't do much about it, right? So this is sort of one problem we are facing in the US. And I think this is also where sort of this more systematic approach helps us, where we need to sort of start narrowing down things. Okay, what are the needs? What do we need to address? Where are the gaps? And these kinds of things. So that's why I think this document also helps.
Right, and Christian?
Yeah.
In addition to that, one of the issues or that one of the problems that happens there is looking at it from end to end, the resilience. While the vendors may meet the letter of their contract, if you're looking at it from the application side, while the hardware may be resilient to that specific letter, looking at the applications being able to deal with that is another problem, because quite frankly, at the end of the day, the application folks that are running on these machines are concerned about getting their science or their work done. And that's while you would think that coincides directly with the hardware uptime or the resilience of the hardware, it doesn't always quite match. There's some issues there, disconnects that mean, sure, the vendor met the letter of the contract, but as far as the application person was concerned, their job didn't complete or they didn't get their work done. And so, that's another issue too.
Yeah, I agree. All right, so if we don't have any further questions, I would like to move to the next talk. The next talk is a paper that was submitted, reviewed, and accepted. It's by Alessio, Burrello, Daniele, Pagliari, Andrea Bartolini, Luca, Benini, Enrico, Macii, I think, and Massimo, Poncino. The title of the paper is Predicting Hard Disk Failures in Data Centers Using Temporal Convolutional Neural Networks. And I would like to ask the host to queue up the video for this.
So,
Yeah. Oops. Yeah, that's the video. Thanks.
good morning, everybody. I'm Alessio Burrello from the University of Bologna, and in this talk, I will describe the work done in collaboration with the University of Torino about our paper that is predicting hard disk failures in data centers using temporal convolutional networks. First, let's describe the scenario that we want to address. So let's consider data centers with many racks of hard disk. Some of these hard disks will be active hard disk and some will be hot spare ones. One of the problems of these systems is the sudden death of the hard disk, because it can cause loss of data and interruption of service of the system. So to solve this problem, what is done is to implement some types of redundancy, so different RAID levels of the racks of the hard disk, and use some hot spare hard disk that can be used to replace failed hard disk in real time. However, what can happen is that the cost of this hot spare hard disk can increase so much in case that hard disks are not much reliable. So a way to solve and to relax a bit this problem is to use a kind of prediction algorithm to predict when the hard disk are going to phase, and then program a series of maintenance interventions that are not uniformly distributed in time, but are distributed in time based on the number of hard disks that this system is going to predict to fail in the next month. So what we can do is to collect a series of smart features that are features related to the state of the hard disk, like the temperature or reading of hard disk blocks or cycles to read the data and so on. And then give this feature to a prediction model that, trained on past data, is able to predict the failure of the hard disk. Then we can use this kind of data to go back in the loop, and so create a closed loop prediction maintenance system that gives a feedback to the hard disk and say when an hard disk is going to fail, to advise and then to advertise the system manager to schedule an intervention in the substitution for that hard disk. So the scope of our work is the application of deep learning techniques to this problem, and the use of this kind of prediction to model the remaining useful life of the hard disk, and the creation of a framework for the efficient scheduling of the system maintenance. Not that using this kind of deep learning algorithm can reduce the number of hot spare disks and better schedule the maintenance, and hence reduce the maintenance cost of a data center. In this talk, in the rest of this talk, I will first introduce the monitoring system, and I will describe the dataset that we used to train our algorithm and test our algorithm. Then I will briefly introduce the pipeline of future selection that we used and the imbalance management of the data, composed by a correlation analysis and the ranking of features to reduce the number of features used in our system, and in some techniques to overcome the problem of the low number of failed hard disk over the total number of hard disk that we have. Finally, I will talk about the results, and I will describe the false alarm and the hard disk failure prediction trade-off, where we compare our method with some state-of-the-art methods taken from the literature. So let's start from the dataset. For our problem, we used the Black-based dataset, that is a dataset that is public and is shared by the Black-based data center. This dataset contains many types of hard disk, more than 20 types of hard disk, with thousands of samples for each hard disk. For our analysis, we only select a single model of hard disk, since it was the ones with the more number of hard drive and the more number, in the highest number of failed hard drive inside the dataset. What we have is more than 1 million of samples of hard drive that are not failed, or better, that will not fail in the next days, and only 7K of failed samples. Note that to create our dataset, we use 90 days of signals from these smart features for each samples, and as a label we use the failing time of each hard drive. So if the hard drive is going to fail in the next 7 days, as you can see, we signal an error, so a failed hard disk in this sample. Otherwise, if we take 90 days and in the 7 days after the hard drive is not going to fail, this sample is classified as not failed hard drive. Then what we did is a first feature selection process to reduce the number of features that are contained in data. All the data inside this dataset are composed by a total of 90 smart features for each sample and for each day of the year, for more than 4 years. So the first step is a correlation analysis done on the smart features, and features that are more correlated and has a Pearson correlation coefficients higher than 0.99 are eliminated from the dataset. In this way, we can eliminate 45 features, since for each features, both the normalized and the raw value are collected. Not that these two values are collected because the raw values should be precise for a type of hard disk, so cannot be compared with other type of hard disk, while the normalized value is a number that the producer of that disk gives to the consumer to compare these smart features to the smart features of other hard drive models. Then, after this first halving of the features, we filter out all the smart features which has more than 60% of NAN values. This is because we do not want to have much data with missing values, because otherwise the prediction could be somehow biased by the values that we substitute instead of these NAN values. Finally, we reduce these 25 features to 18 by selecting only useful features and relevant features for the distinction between failed and not failed samples. For doing this, we use a t-test on each features, and we keep only the features that can distinguish the two categories with a p-value lower than 0.01. So after selecting these 18 features, we again manage the training dataset to correct the imbalance that is created in the training dataset. In fact, as you have seen in the previous slide, the initial dataset has only the 0.7% of the data with the failed class. The original dataset is hence oversampled to both increase the number of samples in the training dataset and balance between the not failed class and the failed class. Note that this is only a way to balance the dataset, because you can use both oversample and undersample way to balance the dataset. In the first case, what you do is to augment the class with the lower number of samples, and what you do is to create new artificial samples from the minor class. Otherwise, on the other hand, when you use an undersampling technique, what you do is to only takes part of the data from the majority class. For example, if you have a dataset composed by 100 samples of the normal class and 10 samples of the failed class, using oversampling, you will have a new dataset with 100 samples for each category. While when you use undersampling, what you obtain is a dataset with 10 samples for each category. So, to favor the training of deep learning algorithm that usually needs a lot of data for training, what we do is to augment the training dataset and hence increase the number of samples by using an oversampling technique. The one that we will use and propose with comparison with undersampling technique is the SMOT, that is the synthetic minority oversampling technique. That is an oversampling technique based on new artificial and synthetic points of the minority of the class with the minor number of samples that are taken in the links between points of the training dataset. So what you do is to draw some links between neighbors of the training dataset and keep random data on this link, as you can see here in the figures. The majority class instead is not modified by this algorithm. As you can see from the figure of the right, what happens after the SMOT after the SMOT application is the augment of the minority class. Here the example shows 3 different classes. So what happens is that the class with the higher number of samples doesn't variate, while the 2 classes with a lower number of samples have a higher number of samples. The effect of this technique on the dataset is demonstrated in this graph, where we show both that the false detection rates is lower, also up to 32%, when we compare the classification done using the SMOT on the training dataset, while compared with classifications done using the raw training dataset with 3 different algorithms that are the Temporal Convolutional Network, a Recurrent Neural Network, and the Random Forest that we will after introduce. The other effect that we can observe is that using undersampling compared to the case always of not using any resampling technique cause a very high number of false alarm rates, so of hard drives that are predicted as failed but are not failed. That is from 9 to 20 times higher with respect to the normal case. On the other hand, if we use the SMOT technique, what we obtain is only an increased FAR of less than 2 times, while we achieve a higher FDR of 32% with respect to not using any resampling technique. So, going to the last part of the presentations, so to the result of our algorithm, what I will describe are a couple of state-of-the-art methods that are compared with the temporal convolutional network that I will introduce, and I will describe the possible embedding of this network. So let's start from a brief description of the algorithm. The first one is the temporal convolutional network, that is the algorithm that we propose in our paper to solve this problem in the most efficient way. The temporal convolutional network is similar to a classical convolutional neural network. It's a feed-forward network, but the principal difference is that the convolution are not 2D, but are 1D. And as you can see in this graph, there is a new factor introduced, that is the dilation, that is here described with the letter D. And it means that in the weights filter, we do not multiply always near pixel, but we miss some pixel in the input data, and we jump to the next one based on the dilation parameter. The effect of this factor is to increase the history of the signal with respect to filters that does not use the dilation. Not that the number of parameters inside the weights are constant, but the dilations allows to increase the history of the signal analyzed without increasing this number of parameters, which is important to reduce the computation. Then the first techniques that we use for comparison is the long short-term memory network, that is a recurrent neural network. It is famous in the field of sequence modeling, since it is natural to model time with this kind of network that presents some recurrent connections to take into account the past history in the prediction of new samples. Finally, we also use a random forest, which is being demonstrated in literature to be effective for this task, which can, however, not take in consideration the history of the signal, but takes single days of the dataset to predict the future, and so the phase of our network, of our temporal convolutional networks. We design a network with 3 blocks. For each block, we have 2 convolutions and a pooling layer, and each convolution has 3 times 1 filter with different dilation factors. For classification, we use 2 blocks of fully connected layers with batch normalization and dropout for regularization, and a final fully connected layer with 2 outputs with 2 neurons, one for the normal class and one for the faded class. So also our algorithm, all the metrics that we introduce are made for correctly compare imbalanced dataset without any biases inside this index.
So it appears that we don't have any audio anymore.
I can hear you. Yeah, I can't hear the
So,
presentation.
so this is, I think, at the source of the presentation. I would suggest the host to put the video maybe a minute back and see if it's probably a replay issue on the host side. Yeah, just run it again. We are still not hearing anything.
Index. The first one is the false detection rate. That is the true positive over the sum of true positive and false negative. So the samples that are correctly classified as failure over the total number of samples that are that comes from the positive class, so from the failure class. Then the false alarm rate, that is the number of false positive over the total number of false positive and true negative. So it is the number of incorrectly classified normal samples as failures over the total number of normal samples. Finally, the F1 score mix all these four parameters to obtain a measure that gives an overall score to the algorithm, to compare different algorithms and select the best one. Not that we use the F1 score and not the accuracy, because the accuracy can be strongly biased from an imbalanced dataset. For example, if we consider a dataset with 99% of a class, if I always predict that class, I will have 99% of accuracy, which is, of course, not a good prediction because I never predict the second class. Now going to the predictions, so to the classifications that both our temporal convolutional network and the state-of-the-art methods made, we compare the random forest applied only to single days data, and the temporal convolutional network and the long short-term memory network applied to input windows with a variable number of days from 1 to 90. The first things that we can see is that the false detection rate increased by more than 9%, going from 1 day of data to 90 days of data as input, and the false alarm rate is reduced by an order of magnitude. After, what we also notice is that changing the input window dimension from 24 days to 90 days, the LSTM see its prediction only increased by 2.5% in terms of false detection rate, while the temporal convolutional network see an increase of more than 8%. This can suggest that the temporal convolutional network can model a higher and longer history of the signal, and can take information from the past, see an increase of more than 8%. This can suggest that the temporal convolutional network can model a higher and longer history of the signal, and can take information from the past better than the LSTM. Finally,
So the video stopped now. It worked fine for us.
Looking at the best prediction for each model, we see that the temporal convolutional network outperformed the LSTM, achieving 7.5% higher false detection rate and 7.4 times lower false alarm rate. Further, what we want to show is also a comparison of the LSTM and of the temporal convolutional network with a varying number of layers and of the width of layers. So here we show two different architectures with more layers and lower layers that you can also better check in the paper, and with varying these kind of parameters, so the number of filters, the width of the network, and the number of parameters inside the filter, we can obtain different classifications, so different false alarm rate, false detection rate, and F1 score, with a different number of parameters inside the network and number of marks. The things that we want to highlight in this graph is that also with a small TCN, so having lower than 10 to the 6 max and lower than 10,000 parameters, we can yet achieve 80.3% of F1 score. That is yet acceptable in this type of task, with lower than 0.1% of false alarm rate. So the things that we want to investigate in the future of this work is the possibility of embedding this algorithm on the hard drive itself, so on the hard drive controller, which is normally a microcontroller of the hard drive, and automatically send maybe a small report with the status of the hard drive. So to conclude, what we present in this talk is that using the SMOT technique we can improve the false detection rate while not paying so much in terms of false alarm rate, that the TCN outperforms all the other methods in terms of different metrics that are useful to benchmark dataset with unbalanced training dataset. And finally, we show that a TCN that is very small, so with lower than 10,000 parameters, can optimally classify this type of failure of a failed hard drive, achieving an F1 score that is higher of 80%. So thanks for the attention, and if you have questions, you can ask now. Thanks.
Hello everyone, my name is Valentin Lefebvre.
So let's give a virtual thanks to the speaker. This was a very good paper. Yeah, thanks. Any questions? Feel free to ask them in the chat. I have a few questions. I'm assuming some of the authors are online. So in terms of, have you thought about making this public in terms of the actual networks, so that people could download this, deploy this in their data centers, and actually check whether your networks, the prediction, are correct? What I'm literally meaning is downloading the network such that you are able to confirm whether what you have learned from one data set applies in a different data center to potentially different hard drives, or whether there needs to be some new learning as well when you deploy this to a new data center.
Hello, can you hear me?
Yeah, we can hear you.
Okay, I'm Daniele Pagliari. I'm the second author of the paper. And first of all, I want to acknowledge Alessio, who was the guy who made the presentation, and he also made most of the work for this paper, and also all the other co-authors. And concerning your question, the code for our model and training algorithm and everything is already public, and it's linked in the paper, I think. No, actually, I checked this morning, and it is linked in the paper. But I want to point out two things. One is that this is a Python code and is not, I mean, production code. The embedding this kind of algorithm directly in the data center or cluster is something that we plan for the future. Right now, we just wrote some, scripts in Python to test the models. So you can use it and you can replicate our experiments, but then if you want to use it in production, of course, there is some work to do. And the second thing is that, as we write in the paper, our work and also all the previous state-of-the-art on this data set and in general on predictive maintenance of hard disk, they train the system on an individual model. So we did the same here, and we selected one particular model because it had a lot of failures. So if you want to deploy this system in your data center, you have to, of course, you have to retrain your algorithm if the hard drive model that you have is different from what we use, because let's say the failure modes that you can extract from these smart features, they change a lot from one model to another. So it's very difficult. We tried, but we didn't succeed in training a single model that can predict different brands of hard drive. So you need a special model for each, a special neural network for each hard drive model. This is the point. I don't know if this answered your question.
Yes, it did actually. Thank you very much. Yeah, it's a good answer. Yeah. So there was one question regarding the whether the input data set is released as well.
Oh, the data set we use is from a company called Blackbase, and it's public, so you can use it. It contains 4 years of data for different hard drive models. And as I said, we selected just one model. And
yeah, so that was a question by Peter, and the next question by Peter was, could you estimate the savings in terms of US dollars or saved server hours? So this is something that we have been also asked with other papers recently to give some indication about how much money this would save. And the problem here is, of course, you're preemptively selecting disks that should be replaced because they're about to fail. And I'm assuming these disks are still on RAID systems, right? So that I'm not sure if you're avoiding serious RAID failures here, or you're just basically managing sort of the RAID system, right?
So what in the paper, we tried to do something like that, but I will admit it's a rough, let's say, rough estimate of the saving. What we said is that you can assume that for a given fault detection rate, this corresponds to a proportional reduction in the number of hot spare drives that you need, because if you can correctly anticipate, let's say 90% of the failed disk, which is what we do, you can reduce by 90% the number of hot spare drives. Of course, this is not actually true, because you need to keep some confidence, to some margin to avoid that if one day your algorithm is not performing particularly well, then you cannot recover the failure. So, but in general, we can say we said that we can assume that it is a given fault detection rate can correspond to a proportional reduction in the number of hot spare drives. So the active drives, of course, don't change, but the spare ones can be reduced. This is what we do, but we wrote in the paper, but we are planning on doing more detailed cost analysis in the future, because we have now, after this work, started a collaboration with an actual public data center in Italy. And so they will give us much more data to train our algorithm, and also help us in estimating the real saving that we can get in terms of euros.
Okay, so the next question is, are the patterns consistent across models within a single brand without needing to retrain the? Yeah.
Actually, this, I'm not sure if we did an actual experiment on this, but I think we tried with a similar model from the same brands, and it didn't translate so well. So I think what is possible is that, and also this is something we want to, we have many directions for future work, and one of them is see if we can use a transfer learning method. So we don't need to train again from scratch the algorithm, but we can transfer the knowledge from one model to another model by just running, you know, a few shots of fine tuning, few epochs of fine tuning of the model, and recover the accuracy we have. This is also something we want to try in the future. So we, at the moment, I don't want to say anything, let's say, final on this. I think even different models from the same brand will have will need retraining, at least partially. This is my personal belief, but we didn't confirm this for the moment.
Okay, thanks. Any more questions? If not, we will thank the speaker again. We now basically go into the virtual coffee break. So everybody can take a restroom break, maybe check their emails, but also use this time to talk to each other on the Slack channel, and potentially even just via the video chat. This is a great opportunity also to change ideas. Typically, we would be also talking about, hey, how you got here? Did your flight were late and so on? We probably won't be talking about that, but feel free to use this half an hour or to basically talk to each other, exchange ideas and so on. We will start up again with the second session of this workshop at 1/2 past the hour, and we'll then continue with the second paper.